All right, hello, and it is currently, as you can probably see, Monday, the 24th of August. So, tomorrow I will be sitting for my chemistry prelim practical exam paper 4. So, as it's the eve, I'm doing a bit of revision myself. I thought I would film this and take you with me as I revise a bit of energetics practicals. So, I know Hwa Chong, and in fact, a lot of schools they like to call it thermochemistry, but really it's just the same thing. I call it energetics because in general, I like to revise my theory and my practical together. So I may do a separate video for kinetics. I'll see how it goes as we go throughout this afternoon. And yeah, I'll see what I get up to and see what I end up filming. So basically, for thermochemistry experiments, there are three different types, okay? So usually the most common thing that they ask you to do in a practical is find the enthalpy change of neutralization. So in order to determine the enthalpy change of neutralization, there are two methods that you can use. One of them we call the continuous variation method, and the other one is the temperature thermometric titration. So as I said, both of these, the point of them is to measure specifically the enthalpy change of neutralization in a particular acid base reaction. So acid base doesn't necessarily need to be aqueous acid and aqueous base. They can ask you to have maybe I don't know they can ask you to add sodium hydrogen carbonate or sodium carbonate crystals, a solid, to aqueous HCl or something. So you have to be prepared to add anything to anything and be able to actually measure. Okay, but usually for these two, we assume that we are working with aqueous solutions. So in general, these two are the ones that for measuring enthalpy change or neutralization. The last part is the one that we're probably most familiar with. If you are my batch in Hwa Chong, we all took the TPE practical. Our TPE practical in 2026 was actually last year's A-level paper 4, by the way. And basically, that one, the energetics experiment, if you recall, they tested us the temperature correction method. So temperature correction, okay, doesn't need to be on enthalpy change of neutralization. It's just any general enthalpy change of reaction. Okay. Give me a moment while I go and get something to refer to, and I'll talk you through each of these three types of experiments. Okay, hello. I'm back. So, I paused the video for a bit there because I didn't want to bore you to death waiting for 1 minute in total silence, seeing me try and fail to draw a table. So yes, this is what the table for continuous variation should look like. Can I emphasize that in the lab, right, there are two types of thermometers. You will get one thermometer where the smallest division on the thermometer is, if I'm not wrong, 0.1 degrees. And then there's another thermometer. If I remember correctly, please don't take what I'm saying now. I'm just saying from memory. There's one thermometer where the smallest division is 0.1 degrees. And then there's another thermometer where the graduation is 0.2 degrees. So you need to be careful of which thermometer it is that they ask you to use. Okay, this applies throughout all energetics experiments, by the way. So basically, right, no matter which thermometer the question just asked you to use, okay, 最重要就是听话 follow instructions. Okay, so for this column and this column, where you actually is just this column here, when you read off the thermometer, can you please remember to read the thermometer to half the smallest division? You can read any apparatus to half the smallest division. Please be very careful of this, okay? And then uh the way that continuous variation works, right, is you can vary volume of Fa2, you can vary volume of Fa3, but these two, you must make sure that the total volume must be constant. So I say Fa2 and Fa3, one of them can be acid, one of them can be base. Please do note which one is which, okay? Read the question first. At the start of every question, they will say Fa2 is this, Fa3 is this, Fa4 is this, Fa6, Fa7 is this and that. Okay? Please read that part. You should be very familiar with how a chem practical should look by now. Okay, now, yeah, as I said, basically, the reason why I've drawn 6 rows here by right, when you're doing your planning, okay, when you're doing your planning, you only need 5. But for some reason, usually if they are asking you to do this as a practical rather than as a planning, 他们通常会给至少6个。Okay, so as I revise the practical bit, I will also advise the planning. I will also revise a bit on the planning parts of the experiment. Okay, so basically from here to here, the volume of Fa2 that you add, this one is going to be increasing, and then this one is going to be decreasing. Okay, and then now these 2 columns here, actually these 3 columns, I want to talk about a bit more. When you calculate the weighted initial temperature, this is needed because you are adding together 2 aqueous solutions. They may have different temperatures at first. Now, usually by right, if you are conducting all your experiments on the same day in the same room, 通常 the temperature won't fluctuate too much. But if you take bio, you will know that in bio we are especially irked by people who write in their planning questions that, oh, you do the experiment in the same room means it's the same temperature. So yeah, there will be some fluctuations. To my fellow Hwachongians, you should be very familiar with this type of experiments. I'm going to be referring to the practicals in Hwachong terms, by the way, like the Hwachong numberings for the practicals. So please do bear with me if you're not my fellow countrymen. But yeah, we're looking at practical 4 right now. Practical 4 that we did in J1 last year. Okay? So basically, when you calculate the T weighted initial, you need to find the volume of Fa2 times the temperature of Fa2. So before you add the Fa2 and the Fa3, you need to stick the thermometer into the Fa2, stir, and then record the temperature of the Fa2. As I said, 通常 if it's in the same room, it won't fluctuate too much unless a thunderstorm starts halfway through your paper or something. I don't know. But yeah, there will be minor fluctuations between 0.1, 0.2 degrees, so you need to take this kind of thing into account. Okay, so this term, plus you do the same thing for Fa3. And then you divide by the total volume. So it's total volume of 这个 plus 这个。Okay? So basically, as a result, you are going to get the T weighted initial. And then after that, you read the T max and the delta T, as the name suggests, the change is going to be T max, assuming it's exothermic. Even though we like to test a lot of exothermic reactions in practical, they can also test you endothermic reactions. Personally, I will admit I have never seen energetic spectacle where the reaction that they test you is endothermic, which is to say delta H is positive, delta T is negative. But yeah, it can come out, so please be mentally prepared. Going to be T max minus T weighted initial. And basically what you are going to get is from this table, you are then going to sketch a graph. So you need to be familiar with at least roughly the shapes of the graph for all 3 experiments I'm about to talk about today. You are going to plot delta T degrees over the volume of Fa2. Because remember, ultimately, my total volume is going to be constant. As I increase VFA2, I 不得不 also have to decrease VFA3 in order to keep the thing constant. Agree? So as a result, right, I'm going to draw 2 lines of best fit. So the delta T is going to be this column minus this column, as I said. So for each volume of Fa2, you get 1 value in this column. Then this column is the column that I'm going to use to plot this graph. Okay? So as a result, I'm going to have some lines, something like that. Okay? No, actually, let me use the ruler to show you. Basically, I'm going to have one best fit line. And then I'm going to have another best fit line. Something like that. Because as you approach a neutralization point, the maximum temperature is going to increase. Then because enthalpy change of neutralization is per mole of what? Per mole of water, correct? So basically, at the equivalence point of the titration, which is to say, at once everything reacts fully, you're going to have the maximum delta H per mole of water because like the neutralization, the formation of water is at its maximum at that point. So your delta T is going to be maximum. So you will get 2 things like this. And then you will need to extrapolate. So extrapolation, okay, draw a dotted line, okay? Did they say to use dotted line? Okay, my personal practice is to use dotted line. My tutor, who is Mr. Colin Loy, has no problem with my practice. Your tutor may or may not have a problem with using dotted lines. I don't know. I've never heard any other tutors teach Chem before, so I have no idea. But basically, the paper won't ask you to use dotted line. The paper will just say extrapolate both lines until they cross. But for me, my personal practice is just to draw a dotted line to show the examiner that this is an extrapolation. Okay, it's up to you if you want to do the same thing or not. But I just prefer to stick to my practice, so I will show you my personal practice. You don't need to follow me. Just stick to whatever you have been doing. Okay? Can? So where you extrapolate these lines until they cross, you will get this particular point here. This particular point here. I feel like I'm drawing econs diagram right now. Looks like a DDSS diagram a bit. But yeah. So as a result, at this point where the delta T is the highest, the corresponding volume of Fa2 is going to be the volume of Fa2 that's needed to neutralize. So in this case, I assume that Fa2 is the solution of known concentration. Actually, they can give you Fa2 of known concentration, Fa3 of unknown concentration, or the other way around. But in this case, do you see how this graph is behaving a bit like the no, not this graph. Do you see how this is getting us sort of to the same idea as conventional titration, where you add more and more things of the known solution from the burette. Then after that, you find the neutralization point, and then this volume that you get in the burette reading table is the volume of the thing that has known concentration already. Then the thing in the conical flask is your unknown. Gets? Yeah, you get how it's a similar idea here. So basically, that is it for continuous variation. This is one method to determine enthalpy change or neutralization. How to go from delta T to neutralization is more or less the same across all three types of practicals. I will explain once I am done talking about all three types. Okay, I'm going to pause the recording a bit. I'm going to write some things for about thermometric titration, and I will catch you in a bit. Alright, hello. So for thermometric titration, it's my favorite and actually a lot of people's favorite experiment in all of H2 Chem. Why? Because it's damn fast. So basically for a thermometric titration, it's more or less the same thing as your conventional titration, except for one thing. In your conventional titration, as I said, you have the solution of known concentration in the burette, correct? Then usually the thing that you put in the conical flask is the thing that is unknown, correct? That's the thing that you pipette. But in a thermometric titration, one difference, okay, other than the fact that I got thermometer lah, the other difference is instead of a conical flask, what do I use to perform my titration? Okay, the thing that okay, depending on the practical, they may ask you to just use a styrofoam cup and put in a 500 cm cube beaker. Okay, but for me, my personal practice, when 500 cm cube or 250 cm cube, usually my personal practice, okay, when I have to write in planning, if I will always say, place a styrofoam or polystyrene cup in another polystyrene cup and place both cups in a 250 cm cube beaker. This is the line that I will always write if I'm doing an energetics planning question. No matter which of the three energetics experiments this is, when I'm doing energetics planning, I will always write this. But that's when you're doing planning lah. When you're doing planning, you're the boss, you're the person who's supposed to determine what the experiment is supposed to look like. If you're just doing a practical, the practical may or may not ask you to put a polystyrene cup in another polystyrene cup. 最多 they will maybe ask you put a polystyrene cup in the beaker and that's it. Whether 250 cm cube beaker, 500 cm cube beaker, I'll be honest, depends on which polystyrene cup your school got lah. I really can't comment. But basically the table thankfully is very simple. You just have the total volume of Fa2 added in one column, and then I hope you can see my cursor, I'm not sure. And then you have the maximum temperature reached. So the procedure, please take note of this when you're doing planning, is you record the maximum temperature reached. Okay, which is to say that once again I will have two best fit lines. One before the neutralization point, where my temperature is supposed to increase. Actually, hang on, let me think about this. Okay, you know what? Basically, for this one, I'm so sorry. For this one, you should get a curve. So don't take a ruler out. Don't take this ruler out. Okay? You should get a curve. Your curve should look something like this. Actually, doesn't need to touch axis. You just start from wherever. Something like this. Hang on. My curves are very ugly. Yeah, something like this. And of course, you're going to extrapolate, but it's just that it's a bit hard to draw dotted line when extrapolating. So that should not be the case. Yeah, my bad. I almost forgot. Yeah, that's why I like to film when I'm revising, so that it forces me to recall things I wouldn't normally force myself to recall. So yeah, you will draw two curves, okay? Curves 不是直线，是不直的线。And then yeah, we're going to get a particular volume, we're going to get a particular temperature. And then this volume, once again, is the volume of Fa2. This is the thing of known concentration that you need to neutralize the thing in the in this case not in the conical flask, in the polystyrene cup. Okay, so once again the procedure is you pipette a certain volume, 通常是 25 cm cube for pipette, into a polystyrene cup, and this solution that you pipette into the polystyrene cup is the thing of unknown concentration. Okay, actually they can ask you to do a thermometric titration to figure out concentration, but it's relatively rare. Usually if they ask you to do a thermometric titration or a continuous variation, it's to determine delta H. Okay, and then you put into the burette Fa2, the thing that you confirm plus chalk know the concentration of. Okay, usually they will ask you to add 2 cm cube at a time. So usually in planning you also add 2 cm cube at a time. And you are supposed to add as quickly as possible. Now, here's the part that I want to emphasize, right? When you are doing planning, okay, I'm going to emphasize for planning as well, because ultimately, right, if they give you in practical, that all's well and good, you just follow instructions and be a good. I was about to say be a good boy, but that would be terribly inappropriate to say and I get cancelled. So yes, if if they give you the thing as a practical, just be a good child and follow instructions and be guai. But if they ask you to do it as planning, then you don't have instructions to follow. You are the person who's supposed to give the instructions. So, when preparing for planning, do you need to memorize experimental procedures? Answer is yes. Can you please memorize this? Every time you add, each addition 需要做两个东西 for planning. 第一个 I'm lazy to write. 第一个就是 stir the solution in the polystyrene cup with the thermometer. Okay, if you're doing this in planning, should you use the thermometer with the 0.1 degree graduation or the 0.2? I would say 0.1. Okay, personally, I would use the 0.1. My honest answer is, come to think of it, I have no idea. I'm going to ask Mr. Colin Loy later. But and if I do get an answer from him, I will put it in the description what I found out. But yeah, usually if you have a choice of which thermometer to use, you will normally use the thermometer that has up to 0.1 degree graduation. But of course, in the practical, they might ask you to use the one with 0.2 lah. Personally, in the planning, when I have a choice, I will use 0.1. So with whatever thermometer it is. Second thing, okay, for every addition, make sure you add quickly, add Fa2 quickly into the polystyrene cup, from the burette into the polystyrene cup. These are the two things that you have to write in planning when you are describing a thermometric titration. Okay, with every addition, you have to add quickly and use the thermometer to stir. Actually, right, can you star this? This part about using the thermometer to stir, right? No matter which experiment in energetics you are doing, whether it's this one or later on when I bring you through the temperature correction, you have to, anytime you add something to something else, whether it's add solid to solution or add solution to solution, every time 你加东西, you must use the thermometer to stir. Okay, understand? Anything else I want to nag about for thermometric titration? No. Okay, temperature correction, I'm just going to go through very, very, very quickly, because if you are my fellow Hua Chongyuan, we've done this in TPE practical, so I highly doubt it's going to come out tomorrow. But of course, if you are my fellow Hua Chongyuan and you're watching this in a couple of months and you knew what came out for Chem Prac in the end and it turned out to be terribly wrong, you are allowed to laugh at me. Okay. But yeah, as I said at the start, this was actually last year's A level energetics experiment, temperature correction. So temperature correction, right? The graph looks like this. Graph looks like this. So 3个 experiment 有3个不同的 Okay, I should stop talking in Chinese. The 3 experiments have 3 different graphs with 3 different axes, 3 different labelings, 3 different shapes. Now, the other 2, as I said, I'm talking about enthalpy change of neutralization only. This method, enthalpy change of whatever the hell reaction you want also can. Okay, and this one, I have a stopwatch. So what's on my axis if I have a stopwatch? Time lah. So basically, this is called temperature correction. Because in my temperature correction, the idea is I want to account for heat loss to the surroundings. My handwriting sucks today. So if I want to account for heat loss to the surroundings, initially, I will not add yet. I will record usually every 0.5 minutes up to 3 minutes. So 0, 0.5 minute, 1 minute, 1.5 minute, 2 minute, 2.5 minute. And then at 3.0 minute, I will add the, usually it's a solid, I will add the thing into the thing. That sounded terribly inappropriate, I'm so sorry. And then I will extrapolate. Then after that, I will get something like this. Usually it will go up first and then go down. It will usually be like that. Okay, when I did this practical, which is to say when I did last year's A-level practical as a practical time practice back in May, I drew this. And then I extrapolated. And then I said here, my delta T is like this. Okay? This is wrong, people. This is wrong. I will say it first and I will say it again so that nobody is ever as unfortunate to make this same stupid mistake that I did. Please do not do what I just did. Please do not do cost yourself. How many marks did I lose? I have the paper right in front of me. I think I lost at least 5 or 6 marks in total from that disaster. But thankfully, Chem got ECF lah. So, people, this experiment in energetics, continuous variation, you draw straight lines. Thermochemistry titration, you draw curves. This experiment, even though the graph looks like a curve, don't be stupid, draw a straight line. Then extrapolate to t equals 3.0 minute. This thing, 这个东西才是你的 delta t max. 明白吗? And as I said, you extrapolate it to t equals 3.0 minutes. This is the time that you add whatever it is that you're adding into whatever it is that you originally had. So this one is before addition. And everything after this is after the addition. So the point of this initial straight line here, right, as I said, is to account for heat loss to the surroundings. So that is your temperature correction method. The table, I don't think I need to show you the table. You can just derive this from the graph lah. This one is in the left column. No, sorry. This one is in the left column. This one is in the right column. Okay. Anything else I need to nag about temperature correction? Yeah, the planning procedure is pretty straightforward. Okay. Do recall, right? For this one, I'm going to draw the similarity. So I'm going to go to full screen. Okay, yeah, the reason why I normally don't talk in full screen, right? You can't see it now, but basically you see where my pens here are, right? This bar where my pens are is actually partially obscured by the timer bar that the recording software is using to show me how long I've been talking for. So the software currently tells me I've been talking for 24 minutes and 30 seconds. So I'm sorry to have been so lost. So I know that absolutely nobody is watching, and frankly, I don't know why I'm talking so much for a grand total of what, 11 subscribers? I lost count. Anyway, this is where I'm going to start to nag about the similarities. This one, continuous variation and temperature correction, need to extrapolate. Thermometric titration, don't need to do extrapolation. Okay? These two, is enthalpy change of neutralization. You plot on the axis its volume of whatever it is that you're adding. This one, it involves a stopwatch. You plot time on your horizontal axis. Okay, this one you plot delta T. This one you just plot T, and then you read the delta, you read the change in temperature of the graph, this vertical distance here. Okay, is everybody very, very clear about the differences between the three experiments, the similarities and differences between them, what the graphs look like? Clear? Okay, there's nothing else I need to nag about. Okay, now for the exciting part. How the heck do I calculate delta H? Two equations. You have seen these two equations before. I'm going to do a bit of nagging and then I'll call it a day for this video. I will see what else I can film this evening preparing for Chem Practical. Okay, so basically, what does this mass refer to, people? Mass of what? Mass of aqueous solution only. My handwriting sucks. Now, this refers to the mass of aqueous solution only. C, this specific heat capacity is just 4.18. I don't think I need to elaborate further. Delta T, okay, you know what? I'm going to switch to this red that isn't very visible on dark mode. This delta T, okay, is the one that you get from here. Is the one that you get from here. No. In this graph, the delta T is... In this graph, the delta T is like that. Okay? This graph, the delta T is just like that. So everything I've circled in red is the thing that you plug into this delta T here. Okay? So remember, mass is the mass of aqueous solution only. So, people, if I add 4 grams of solid into 25 cm cube of aqueous solution, let's say I add 4 grams of NaHCO3 crystals into 25 cm cube of HCl aqueous. What is M? M is 0.025. Okay? It's not 0.025 plus 4. Actually, 25 cm cube is too little. Maybe let's say 100 cm cube. Okay? It's just the volume, the mass of the aqueous solution. And you can just assume that the aqueous solution has the same density as water. Okay? C is just specific heat capacity of water. If they don't give you, just use 4.18. Actually, what's the data booklet value? Let me check my data booklet. According to the data booklet, C is equals to 4.18. Yeah. If they don't give you, just use the data booklet value of 4.18. If they ask you to use 4.2, just follow instructions. Quite use 4.2. Delta T, I showed you where on the graphs to read off already. I hope you are clear on this. And then delta H is just this over number of moles. There's no negative, I'm sorry. Actually, let me put a plus minus here. Okay, this number of moles is the number of moles of the limiting reagent. Okay, I say again, this number of moles is number of moles of the limiting reagent. Clear? That's how I get my delta H in kilojoules per mole. I divide by mole. Okay? Last thing I want to nag about, this plus minus. Remember, if it's exothermic, I give out heat, my delta H is negative. If it's endothermic, I lose heat, my enthalpy change is positive. As I said, usually, they will test you exothermic reactions. So remember to put the minus, but it can also be plus. It's just that 我没有看过. Okay? Clear? Fantastic. Yeah, I'm sorry to have waffled on about energetics for half an hour, but I hope we are clear. And just one more thing I wanted to talk about. Even though it's not related to the video, I have I mean, there have been a couple of people commenting on the videos. There have been a number of people who have subscribed. So I just wanted to say thank you so much for your support. Even though my channel is, I'll be honest, I don't really care that much about the channel. For me, it's just a place to dump my videos of myself revising. And for me, recording videos for you guys is also a very good way for myself to revise. I've got an exam tomorrow. I'm revising right now. So yeah, about the future, I will just film anything that I get up to. anything interesting that I feel that I want to revise, that I also want to film and talk about for other people's awareness, I will film and talk about as well. And basically, that's the plan from now all the way until A levels. Okay? Yeah, thank you very much for being with me for the past half an hour, and I will catch you hopefully later today talking about some other chem thing. Bye bye.